Good afternoon, everyone. I am Khushi Chauhan, a doctoral student at the Department of Biochemical Engineering and Biotechnology, and I have the distinct pleasure of being your host today for the event Know the Nobel Laureates 2025, presented to you by Academic Outreach and New Initiatives and Research Synergy Forum, IIT Delhi. This event is dedicated to the world's most prestigious award, the Nobel Prize, and the revolutionary knowledge they celebrate. Every year, the Nobel Prize recognizes individuals and organizations whose work has conferred the greatest benefit on humankind. Today, we bring the essence of this year's prize directly to you, featuring experts who will illuminate the research and ideas that captured the world's attention. The program today is structured around the six pillars of the Nobel Prize. We are honored to host one eminent speaker per category to talk about the precise subject or the revolutionary breakthrough that earned this year's Nobel accolade. We will follow the event's traditional sequence of announcement of the prizes, starting with physics, followed by chemistry, physiology or medicine, literature, peace, and economic sciences. Before we commence our program, I am honored to invite Professor Ashwini Agarwal, Dean Research and Development at IIT Delhi, to share his perspective and officially inaugurate our event. Please give a big round of applause for Professor.
So it's an exciting event and an evening. And I'm very happy to be part of it. Something which we all read in the newspapers, but we don't get to really understand unless until we are connected to that area, then probably we know. But as an outsider to various areas of research and technology, it's often very intriguing to know what led to that Nobel Prize. What is that they did which could fetch them such a great honor, which is internationally recognized as one of the best prizes in this category, in these categories. So you all know these Nobel Prizes have been established because of will of Alfred Nobel, who actually invented dynamite. So the story goes, I don't know how much true it is, that he read his premature obituary which said, "Merchant of Death is dead," and which made him very concerned about it, not to be known in this fashion. And then he left his fortune to be used for prize for doing research which is best for humankind. So I think that really speaks that how the mind change and how the ambition of just making money and not working and thinking about the humanity can turn into something which is a more contribution for the benefit of the humanity can happen. And I think all of us should learn from that, that whatever we have done, whatever we are doing, we should aim that our research, our efforts should benefit the society at large. And that is where we are. ITs are made for that. And I think we owe to the society that we do something and return it back to the country. As far as uh, my my contribution goes in this institution, I took over as Dean R&D in only April, and what I am planning and envisaging or targeting is to make the life of researchers a bit better at IIT Delhi. So we are all concerned with administrative work, the purchase problems, the accounts problems, and things like that, which really hamper the innovation, the spirit of innovation in us. And sometimes we hear that we don't want to do any more research because it's so difficult to get money and spend it and use it properly. So my vision is, by the end of my term, if I can make this place a little better place for myself, that means when I am not a dean, my papers and my bills and my projects are handled more efficiently, I think then I would have done my job. So we in administration have a responsibility of make this place better for researchers who can probably bring Nobel Prize for us in future. I was also just looking after that almost 12 people with Indian Connect have received Nobel Prize up to now, and that means that we can do, and possibly we should do. Although Nobel Prize comes without making an effort for it, it comes because you are interested in science. It comes because you have done something which you are passionate about. Because those people who have tried to do everything to get a Nobel Prize probably did not get it, and so we have not to really take a path to get a prize, but take a path which is something should be done for the society and for the science, and hopefully these prizes, this or other prizes, will follow you. So with my best wishes are with the speakers who are going to do a very tough job today of explaining us what they have done, but I'm very sure we'll learn, and I will stay back and try to learn also. And thank you so much for sparing time, my colleagues who will be speaking here, and making it work for us. So thank you so much.
Thank you, sir, for your insightful words and setting the tone for what follows. So, the 2025 Nobel Prize in Physics was awarded to John Clark, Michel H. Devoret, and John M. Martinez for their work demonstrating macroscopic quantum tunneling, bridging the bizarre microscopic quantum world to systems large enough for us to observe and interact with. To guide us through this fascinating subject, we welcome Dr. Kaustuv Manna. We welcome Dr. Kaustuv Manna, a faculty at the Department of Physics at IIT Delhi. Dr. Manna earned his PhD from the Indian Institute of Science, Bangalore, and then served as a group leader at the Max Planck Institute in Dresden, Germany. He has been awarded the Max Planck India Partner Group Award in 2021. Dr. Manna's research focuses on emergent quantum phenomena, and his work, which combines advanced crystal growth with complex measurements, has led to over 80 publications in premier journals. Please welcome Dr. Kaustuv Manna with a round of applause.
Good afternoon, everyone. So first of all, I would like to thank to the organizers for giving me opportunity to speak here today, and I'll start my talk. So, as you all know, like in 2025, Nobel Prize is given to these three great scientists, Professor John Clark, Michael Devore, and John Martinez. So, to be specific, the reason for is the phase is for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. This sounds little bit abstract, but when I go through the talk, I'll try to explain in simple terms how you can understand the importance of the discovery in our today's world. Like okay, so in 2025, this year is announced as the International Year of Quantum Science and Technology by United Nations, and this is because 100 years back, around 1924-25, the basic equations of quantum mechanics were being developed by Max Born and de Broglie, Heisenberg. So they were developing the basic equations. So in honor to that, 2025 is announced as a national the year of for 100 years of celebration for quantum mechanics. But it so happened that I do not know whether it's a coincidence, lucky coincidence, or whatever. This year's Nobel Prize is given to people who build the first frontier, the milestone that started the using the quantum mechanics in a macroscopic level, so that our modern days the quantum computers are being developed. So the reason or the most foundation stone are made by this major discovery, based on which the today's 2025 Nobel Prize is given for that. Now, In this modern day, the quantum computers, whatever is being developed so far, like in IBM or in Google, the team which are leading there, the people, they are actually the student of these people. And why it is so important to say that, I will give you just one example. For say the Google's Willow chip, it is says that one algorithm which the more like the today's binary computer, the most powerful supercomputer, if it takes, let's say, 1 septillion years, like 10 to the power 25 years, this computer can crack that in 5 minutes, just 5 minutes. This is so fast. You can understand why it is so fascinating. And in 2025, Nobel Prize is given the people whose experiments started this work. So so this now I would like to go to their work, what they did in 1945, sorry, 1985, 1984, the fundamental papers, where they did the experimental work, where they saw that this quantum tunneling, which we observe in the atomic level, we can trap, we can control those properties in macroscopic devices. That is important, that we can observe those properties and we can manipulate those properties for our whatever desired application. So based on that foundation stone, now we are developing the quantum computers. Now, before going to their actual setup, experimental setup and results, first, as I can you can see that I want to discuss these two important part, what is quantum tunneling and what is energy quantization, so that we can understand their experiments much better way. So quantum tunneling, what is quantum tunneling? In classical world, let's say we have a potential wall. So potential wall, so it can be, let's say we are standing in front of a hill and you want to cross the hill, so you have to climb the hill and you have to go from one side to other side. Or let's say you want to throw a ball from one side, so you need to throw the ball so much kinetic energy that it is larger than the potential energy of this wall, so that ball can cross from one side to other side. So this is the classical picture, but quantum mechanics does not follow this rule. In quantum mechanics world, it is possible that this ball can tunnel through, irrespective of whether its energy is so high or not. There is always a possibility that this will cross through that barrier and reach to the other side. Now, in our daily life, there are many ways how you can understand this tunneling effect, quantum tunneling. There are many examples. For example, STM. So in STM, we have scanning tunneling microscopy. So your probe, you can bring it very close to your sample and you can map the sample surface. You can actually observe those atoms, and if you observe them, you will see that in between the atoms there is lot of space available. It's not solid. So the solid material like this, it is not actually solid. If you go to the atomic level, at least 70 to 80% it is filled, but those 20%, whatever is empty, if your particle is small enough, it can pass through. But there is a catch. These particles, when it passes through these cavities between these atoms, it will experience electrostatic force, huge force, nuclear force. It has to overcome that force. Then only it can cross the tunneling, it can tunnel through the material. Otherwise, it is not possible. Another example is the nuclear fission in sun. Why sun is so so much energy? What is the source of so much energy in sun? That is actually quantum tunneling effect. Second is the nuclear fission. Let's say you have radioactive particles like uranium or polonium. It decays. It's a radioactive material is very unstable. So it decays into alpha particle and goes to a much stabler atom. But why the particles does not spontaneously decay? The lifetime of this uranium or polonium, whatever radioactive elements, 10 to the power 10 years. It takes 10 to the power 10 years to decay. Why it is so? Because if the alpha particle want to come out from the nucleus of this radioactive particle, then it must overcome this energy barrier. How much energy barrier we are talking about? 10 to the power 25 mega eV, and the alpha particle has energy just over 10 mega eV. So how this alpha particle is coming out from the nucleus? This is a classic example of quantum tunneling. Irrespective of lower energy of alpha particle, it can tunnel through the nuclear barrier and it can go from one side to other side, because at that atomic level there is a wave particle duality. The particles behaves like waves also, and for the waves the probability that matters for us. Probability is never zero when it crosses to the other side. It can be 10 to the power 1, 10 to the power minus 10, 10 to the power minus 20, whatever value. But as long as it is not zero, there is a finite chance that the particle will tunnel through that barrier, irrespective of how low energy it is. It doesn't matter. So this is the concept of quantum tunneling, and this is in the microscopic level. Now, whatever we are talking about in the Nobel Prize, this is actually they catched this effect in the macroscopic devices, and we are manipulating the properties, because here the decay of alpha particle we cannot control, but in the devices whatever we are talking about we can control the properties. Next, which material you want to use so that you can observe this quantum tunneling and you can control the properties? The result, the it is actually the superconductors. So the superconductor means, in the conductor, normal conductor, you have the carriers like charge carriers. It can be electron, hole. By the way, hole is not a particle, so if it is the empty state of electrons, so you can consider that there are electrons, but electron means it's a charged particle, right? So electron has a negative charge, so negative charge means it's a strong electrostatic force. So because of which, when in a metal the charge carriers pass through, it experience lot of force, lot of collisions. So it is a ohmic contact, and the electrons are quantum mechanical particle, that means it's actually fermions. So each of these electron has unique combination of quantum states, so it cannot be that all the energy, so the electrons are actually distributed in different energy levels, as you can see here, at in different levels. But if you cool down the sample below a critical temperature, what happens is that electron loses its identity. It now forms a bosonic particle below a critical temperature. Consequently, it forms pairs and a macroscopic entities which you can control. So this superconductivity is discovered in 1911, but until 50 years there was no explanation, absolutely no explanation why certain materials shows superconductivity. So in 2000, sorry, in 1957, then this BCS theory was proposed, because of which they got the Nobel Prize in 1972. This is the only theory ever proposed which explains the origin of superconductivity in these compounds, and until today there are a lot of flaws, but this is the only theory which is available so far, which explains that the electrons it forms, irrespective of negative charge particle, it forms pairs, and when this forms pairs in the entire sample, it forms a macroscopic channel kind of. Now in 1962, then Brian Josephson, he proposed a theory. He proposed this, mind it, he proposed this theory when he was doing PhD. Okay, so during his PhD itself, he proposed a theory that if we use two superconducting wire, make a junction, in between the superconducting wire you put an insulator, then through that insulator these Cooper pairs can tunnel and you can get a current without applying any voltage. Okay, this is called Josephson junction, and this was experimentally observed 10 years back. He got the Nobel Prize in 1973. Now this Josephson junction and the Cooper pairs is being used for making the device which I'm showing the next. What? Next slide. Next slide. Huh? Oh, sorry. Okay, so so superconductor and the Cooper pairs, these are the ones which is used for the device that is used for by John Clark, Michael DeVore and John Martini. So this is the schematic diagram of that device. On a silicon substrate, they produce superconducting wire which makes this kind of crossing, and there is a insulating junction between these two superconducting wires, and this is the device which they use. So there is a copper pipe, and in order to minimize the noise, they use the copper particles, and they connect this wire with a battery, the DC source, and there is a microwave excitation which is connected here. So let me explain to this at this point, that whatever Josephson junction they are using, this is current bias Josephson junction. So earlier case Josephson junction, we didn't apply any current, but now we are applying the current and controlling the movement of this Cooper pair across the device. So what happens is that in this kind of experimental setup, we have the so this potential looks like this, the like a wave. Now so this, whatever it shows the potential, this is not the potential of the Cooper pair, but the potential at this junction, the insulating junction. So it so happened that this slope of this junction you can control by how much current you pass. If higher current, that means slope is higher, so the system can easily this roll down and you can get finite current in the device. But if you can control the current so that the slope is optimum in such a way that your system is trapped in one of the quantum well, in that case, when the particle is trapped, that means it's a situation of particle in a box. So when there is a particle in a box, so the energy states are quantized. It does not have any continuous state. So the energy is quantized. You can have fixed energy levels. And by exciting with the microwave, you are exciting the system from one level to other level. Now, if you can control the current so that your device is trapped in one of these quantum well, then the quantum mechanics says that classically the energy is not sufficient to overcome this well, but quantum mechanics, it is allowed to tunnel through. So this is the quantum tunneling that I was talking about. With the quantum tunneling, and you can, if you can excite to the selective way, then you can get the states from each of these energy levels through quantum tunneling. With the microwave excitation, this is the experimental result of their setup, which shows that if you cool down the system below a very critical temperature, this is actually millikelvin, as you can see 10 millikelvin, where the thermal fluctuation is just negligible. In that very low temperature, you can get each of these excited state, you can excite with microwave excitation and you can get tunneling current, and this current is macroscopic entity. Each of these you can now assign as 1 bit. So each of these energy levels you can have one bit. Earlier case in the classical computer, we have either 0 bit or 1 bit. Just make the combination 0, 1 and all the combination and you do the computation. But now if you can use this as a bit, quantum bit, you see so many energy states are there. You can just excite them, the system from one state to other state. Simultaneously, so many quantum states, each of them can give 1 qubit. Just play with those qubits and you have your quantum computation. So this, based on this concept, the modern days quantum computers are being built in Google and IBM. The major scientists, whoever is leading these projects, they are actually the academic grandsons of these 3 professors. So they are actually leading this project. And the what are the beauties about these quantum computers? So these computers, it is mostly used, for example, let's say if a pandemic comes and you want to discover its medicine, then this computation power can be used to very fast way. You can find out theoretically what can be the best the medicine, or let's say in the battery energy. So nowadays lithium ion is used, but there can be different compositions. You can run the simulation very fast and find out what is the optimum composition, so that you can, if you build the battery, efficiency will be maximum. So these are the cases where these computers can be used. But let me tell you, it is far away from any practical cases. For example, the daily day life, we have the like mini computers, let's say our digital computers, our mobile phone or whatever, it cannot replace so easily, because this works at millikelvin. and it is very prone to little bit temperature fluctuation, little bit noise, it's just gone. The combination, if you, let's say, if you want to crack the encryption of, for example, Bitcoin, you need at least few thousand qubit, and the best quantum bit which is used, which is developed today, it is just 1000 qubits. So each additional qubit, it is exponentially increased complexity to control them. Harmonicity, it is controlled. So getting few thousand qubits is long way to go. So there are a lot of limitations, but this is very exciting. So the people behind this concept, they are honored with the Nobel Prize. So I hope with this limited time I could explain whatever possible, because it takes a lot of discussion each of these concept. So thank you. And one more thing, so I see that there are a lot of students. If you want to understand more about the superconductors and how to control the properties for the applications, in our physics department, a lot of faculties are working in these concepts. And as you know that in India, the government has launched the quantum mission, so a lot of activities going on. So please go through the websites, and you are feel free to contact us, whatever we can discuss. Okay, thank you.
So thank you, Professor Koshta, for making it so simple, and also for the critical analysis that you later presented. It's open for questions. If there are any couple of questions, students. I think it was a pretty clear lecture, so we'll move on to the next, Kushi.
Thank you, sir.
Thank you.
Thank you, Dr. Manna, for the brilliant talk. Please give him a big round of applause. Next, we turn to the Nobel Prize in Chemistry, awarded this year to Susumu Kitagawa, Richard Robson, and Omar M. Yagi for the development of metal organic frameworks. These revolutionary porous materials can be custom designed at the molecular level for applications ranging from harvesting water from desert air to carbon capture. To share insights into this groundbreaking molecular architecture, we have Dr. Kuntal Manna, a faculty from the Department of Chemistry at IIT Delhi. Dr. Manna completed his PhD at Iowa State University and postdoctoral fellowship at the University of Chicago. After joining IIT Delhi, he earned the Mrs. Veena Arora Faculty Research Award and the prestigious Humboldt Research Fellowship for experienced researchers this very year. Dr. Manna specializes in creating organometallic and porous functional materials, holding 60 research articles and 18 patents. Please welcome Dr. Kuntal Manna with a big round of applause.
Thank you. This one? Good afternoon, everyone. So this year, 2025, Nobel Prize in Chemistry is given to three gentlemen: Professor Susumu Kitagawa from Kyoto University, Japan, Professor Richard Robson from University of Melbourne, and Professor Omar Yagi from University of California, Berkeley, USA, for the development of metal organic frameworks, that is also abbreviated and very well known as MOFs. So to the general audience, first let me tell you very briefly in a simple way that what is MOFs, a very general way. So it has two components. One is metal, and then like metal is like iron, cobalt, nickel, zinc, and any other metal, and there is a hyphen. Then the second component, that is the organic, that is made of carbon and hydrogen. And when these two components, metal and organic, they are assembled together, they give a three-dimensional framework, and that is called metal organic frameworks. Very simple. So here I have given one three-dimensional structure of a metal organic framework. So where metal it can be isolated metal ion or it can be metal clusters on the corners. Okay, here in the corners. And those clusters are connected by organic linkers, and the linkers, you can see there are some 6-member cyclic rings. These are actually the benzene ring made of carbon and hydrogen. So this this structure looks pretty good, right? And this is very symmetric, ordered, crystalline. And more importantly, you can see that there are a lot of empty space inside, and those are the pores. So this is a porous material, and these pores are uniformly distributed. So unlike the common solids like woods, sands, bricks, those are densely packed. These type of materials are highly porous. There is a huge volume, empty spaces inside of this material. So these are the porous materials. And because of their high porosity, they have a very high surface area. Just 1 gram of MOFs can have surface area up to 8,000 meters square. That means just 1 gram of tiny amount of MOFs can have a surface area which is close to the surface area of a standard size football or cricket grounds. And that's very impressive, right? So MOFs or this type of materials is not like that it is newly invented, recently known, very hyped material, and because of that Nobel Prize has been given. No. This type of material is actually known for a long time, and one of the earliest example of MOF type material is the Prussian blue, and it is a deep blue color solid. It is frankly soluble in water, and for a long time it was used as a blue paint in oil painting. And here you can see that it also has a MOF type structures which is made of iron in the corners Fe, that is iron in chemistry, and they are linked with C111N, that is a cyanide ligand or linkers, and it also have a 3-dimensional framework similar to MOFs, what we tell. So what these 3 gentlemen pioneered, and because of that they are awarded Nobel Prize this year, is that they first developed some designing principle, scientific concepts, that how to make highly porous solids or materials for various applications using metals and organic linkers. So first, Professor Richard Robson from University of Melbourne, he first proposed that if we take a molecular, he first proposed how to make a highly porous material using the molecular building block approach. So he proposed that if you take a metal complexes as a molecular building block, like he used copper 1 tetrahedral complexes where there are the 4 ligands, copper 1, and the ligands are very labile like acetonitrile. Then if you react that complexes with some rigid tetra-coordinated organic linkers, then you can generate a 3D crystalline framework with cavities inside, and these cavities can be larger and more accessible compared to the traditional porous material like zeolites. And after that, few years later, Professor Omori Ihagi from, at that time he was at Arizona State University in US, he further extended that idea using the reticular synthesis. So what is reticular synthesis? The reticular synthesis is basically the connecting these metal clusters here, what he named as a secondary building unit, with appropriate linkers to give it 3D networks or 3D frameworks in a predictable fashion. So he proposed that if you know what type of SBUs or metal clusters we are using, what type of ligands we are using, then we can design, we can predict the structure of that porous solid, and then we can make it. And that is the reticular chemistry. So in this field, he also made a lot of other development, like the metal organic frameworks. This term, Professor Omori Ihagi first introduced, he coined the term. Not only for that, in the synthesis, this how to make it. In the synthesis of MOFs, he also did a very big development. he used the carboxylic acid functionalized linker. This is the C double bond OH. This is the carboxylic acid groups, and this is very important in MOF synthesis. And this is actually the breakthrough in MOF preparation or making it. So, reticular synthesis, let me tell you further expanding, he also explained properly that in the reticular chemistry, if you know what type of nodes you are using, and if you keep the node same but increase the bond length of the linker, then you can create or make different types of material which has the same structure but pore size varies. So if you increase the, as I showed you in the video, that if you increase the length of the linkers, you can increase or tune the pore sizes larger. Something like here also, this is the zinc based MOFs. Same type of material, the metal is zinc, the first one, the top one, the number one, this is the very famous name is MOF 5. This is a zinc based MOF, cubic structure. Within that there is the yellow balls are there. These yellow balls make nothing. It is just showing in the picture that how much void space, empty space is there. These yellow balls are showing how much empty space are there in the solid. So if you can see in this right hand side, on going from top to bottom, if we increase the length of the linkers, its pore sizes increases, free volume increases. And the last one, that is the IR MOF 16, it has 91% void space. So there is a lot of empty space, and that we can apply this material for various purposes. In the same time, Professor Susumu Kitagawa from Kyoto University, Japan, he also developed many similar types of MOFs materials, primarily for the application in gas storage and gas separations. And one of his key contribution in this field is that making the breathing MOF. So when we breathe in, we expand our lungs and the air with oxygen goes in. And then when we breathe out, the air with carbon dioxide is released and we squeeze the lungs. So same thing like here. So we developed a couple of MOFs which has dynamic structure. In certain condition, it can expand, pores can larger, it can trap gas molecules, and in certain condition, in the reversible way, it can squeeze, make the narrow pores and releases the whatever the trapped gas molecules inside. So after that, in last 25 to 30 years of intense research by many groups around the world, now MOFs are finding applications, commercial applications in various fields. For example, Professor Iyagi's group recently made MOF 801 and MOF 303, which can capture water from air even in a very low humidity level, like in desert area where the humidity level is less than 20%, 10%, it can capture water. So what they did, that they showed that like 1 kg of MOF in a chamber in the night time in the Arizona desert where the humidity level is less than 10%, in the night time when the humidity level is relatively high, it can capture the water, and in the daytime in presence of sunlight, that water converted to water vapor in a closed chamber, then condense, and we can get the pure water. So in that way, like MOF 801, it can 1 kg of MOF 801, it can produce like more than 1 liter of water just from air without using any electricity or no power. That's impressive. And now a company named Source Global, they are using MOF 801 to harvest drinking water from air. And in the world, many groups are also using MOFs as to develop various types of catalysts for various catalytic applications like carbon dioxide reduction, methane oxidation, organic transformations. And nowadays also MOFs are finding potential applications in many different areas like gas storage, gas separations, drug deliveries, carbon capture, mining rare earth metals, sensors, water treatment. And here I have given a list of couple of MOFs which are now being commercialized by various companies Like H-Cust1, the top one, it is now produced in multi-ton scale by BASF, and it is also sold commercially. As I told, that Source Global is using MOP 801 to harvest water from air. And like Calf 20, it is used to capture carbon from flue gas. So the research is going on, and hopefully in future MOP will find many more applications in different areas. And I would say at the end that MOP is a very new class of engineering materials which has a very good tunabilities in many sense. And thanks to the three gentlemen who got the Nobel Prize, Professor Yagi, Rosman Kitagawa, and Robson. And so congratulations to them for getting the Nobel Prize this year. And thank you. Questions, please. Questions, yeah.
Just wait for the mic, Tapan.
I think I can hear. Yeah, please tell.
No, it's also for the recording. So.
Hello. So, are there examples of MOF made of mixed metals?
Yeah.
Mention that thing. So.
Yeah. This is just brief. It is there. Like you can make the MOPs with 2 or 3 different metals. Okay, we are also working on that.
Okay.
Yeah, it is there.
And then another.
It depends on the purposes of the application also.
Another thing I found that when you were showing the Prussian blue, the first one.
Yeah.
They're copper of different oxidation states.
Iron.
Plus to iron. Different oxidation states. So how does it work? And
actually, Prussian blue. When I was in college student, we also did the same experiment in the practically. Okay, in the practical. So basically, this has iron plus 2 and plus 3. So how it is made? Plus iron plus 2 complexes. If you add potassium cyanide, it gives the iron hexa cyanoferrate. That is the water soluble octahedral complexes. Then if you add iron plus 3, then the network comes, and that becomes water insoluble precipitate. And whatever the color you are seeing is a very deep blue color. That's why it is also used for painting. That is the metal to metal charge transfer. Iron plus 2 to plus 3. That's the standard example in chemistry.
Okay. Thank you.
Yeah, origin of the color. Yeah, please.
Thank you for a very excellent talk.
Thank you.
And, a layperson like me could actually understand it. What happens to these kind of discoveries, which are commercialized? Do they then lead to patents? And if so, will we be excluded from commercializing them in our country? And can Delhi IIT lead a movement, to bring this extremely useful technology, which will be useful to tackle climate change to our country?
If it is, okay, if it is patent, right?
Yeah.
That is a, I don't know much, because if it is patented, who is the inventor, he will patent first. Then I don't know much about the patent policy. Okay, so I hope, normally what researcher does, if a patent, I think they sell the patent to the companies who want to commercialize, because that is also related to the money. Okay, it's not like public always. It's depending on the inventors. If I invent a material and if I patent it, it also depends on me. Whether I will remove the patent and it will be generic drugs versus patented drugs. Or I want to give some company, or I can make a company and then I commercialize. So the money will become to the institute and also to me. That depends. Yeah.
So can Delhi IIT bring this technology to India?
Yeah, there are many people are also working on MOPs. If they develop something, okay, for particular purposes, that will be the made of India MOPs. Yeah, definitely. Yeah. Please ask questions.
Quick 3 questions. Chlorophyll and hemoglobin, these are also metal organic, right? No. Chlorophyll has copper. No. But there's no framework.
There is no frameworks. These are called the coordination compound.
Yeah. So
molecular compound.
Okay. So it has nothing to do with MOFs. Frameworks cannot be built.
Actually, people has done like porphyrin iron complexes. They also made in a framework, and they have different property compared to the molecular complexes, mass stability, and there are other kind of things. And many applications has been also explored, like photochemistry. Okay, but what you are talking about, that is the molecular chemistry.
Okay.
that is the molecules.
Okay.
Those molecules are assembled in a 3D way to give a material that is insoluble in water or any other solvent, and that is.
Okay.
Yeah.
Quick, two more questions.
Yeah.
One is related to these MOFs. Today's problem is PM 2.5. Can we make the cavities big enough to capture PM 2.5?
People are doing that.
People are doing that.
People are doing that. Yeah, it has high surface areas. Okay, so it's something like in air filter we are using charcoal and HEPA filter, right, to
Yes.
capture the tiny particles. People are doing this. People are also using zeolites, but MOFs people are. It is under research.
Okay.
It's under research. Yeah.
The third question, which is more philosophical, is that aren't we playing with the second law of thermodynamics? When you showed this example where people are capturing water without using any power from the atmosphere, aren't we playing with the second law of thermodynamics?
No, you cannot correlate with the physics here, so I'm just going to tell what is happening. Yeah, I understand. Okay.
Basically, you're decreasing entropy somehow.
No, I'm just telling. So it has a very high surface area. If the material is highly, let's suppose hygroscopic is a highly hygroscopic materials. Okay. Suppose if you put a salt, okay, like many salts that are very hygroscopic, it can capture water from the atmosphere, and that's why many salts, okay, that it can also liquefy. So those hydrophilic MOFs, which is high surface area, they absorb the water molecules either by electrophilicity or hydrogen bonding. They capture those water molecules in the night time, whatever the devices, it can do this. Okay. So waters are filled within the MOFs, okay, because it is hydrophilic. And what they did, that is published in the papers, and they also commercialized that those MOFs, they now in the daytime when the sunlight is here, so it is heating up, temperature is increasing, so water is vaporized, and there is a condenser. It is basically just condensed in the closed vessel. Okay, and there is one company that I told, that Source Global. I saw the YouTube video. So what they are doing, they are actually integrating this MOF or these devices with the solar power, so that efficiency will be higher. Because this is 1 kg of MOF it can give 1 liter of water per day. It's okay. Still, I mean, there is no without any power. But if you integrate with the solar power, okay, it will be fast. And they are actually doing, and they install the unit in 50 countries. That you are getting the water, drinking water, pure water, added with minerals from the air. And the water problem is a real problem nowadays. It doesn't matter where we are. So water problem is there. Okay. All right.
If
Any
there are
other
no more
questions? Acha, yeah, sure.
Applications in catalysis, what are their limitations compared to zeolites or other ceramic porous materials?
That's a common question when people advertise MOFs. There are certain advantages and disadvantages for both sides. So let me tell what is the advantage of MOFs compared to the zeolites, and then I will tell. So MOFs, as I told, it is an engineering kind of material. Okay, so in catalysis, there are many properties, like MOFs materials are highly tunable. You can tune the pores. You cannot do that easily in any type of other metal like zeolites. It is here, in the same structure, you can tune the pores from micro level to macro level, like meso level. There are a lot of other tunabilities, like suppose in the MOF you have the metal, then you can do the post-synthetic exchange of the metal, you can do the post-synthetic exchange of the linkers, okay. It is highly crystalline, but one of the disadvantages of MOF is the thermal stability. Many MOFs, it can go up to 500 degrees centigrade stability. Stability means the two stability. One is thermal stability and chemical stability. I'm talking about thermal stability. The problem is that here you have the organic part. When you are heating in the presence of air, it will burn and it will give the carbon dioxide and framework will collapse. So zeolite is very good when it is the high temperature applications more than 500 degrees centigrade. But I believe the MOFs are very good in the low temperature because it has also very other features that zeolite cannot have. Okay. All right. Any other questions?
I think we'll move on then.
Okay, we'll move on. Okay.
Thank you so much for making it so interesting.
Thank you everyone for the questions, and thank you Dr. Manna for shedding light on the immense potential of MOFs. Moving ahead, The 2025 Nobel Prize in Physiology or Medicine was awarded to Mary E. Brunkow, Fred Ramsdell, and Shimon Sakaguchi for their discoveries concerning peripheral immune tolerance, specifically the role of regulatory T cells, which act as the immune system's security guards. Joining us to speak on this crucial field of immunology is Dr. Nimesh Gupta, a virologist and immunologist at the National Institute of Immunology, Delhi. Dr. Gupta pursued his postdoctoral research at Institut Pasteur in Paris, exploring the biology of regulatory T cells. Today, he heads a key research group at NII focusing on the T cell determinants for protective immunity. Notably, his team's human immune monitoring platform played a pivotal role in phase 3 trials for vaccines, including Incovac, which is the world's first approved intranasal COVID 19 vaccine. With over 50 scientific publications and roles on prestigious bodies like India's National Technical Advisory Group on Immunization, Dr. Gupta's expertise is both fundamental and translational. Please welcome Dr. Nimesh Gupta with a big round of applause.
Thank you, Shikha. Right? Khushi, I'm sorry. Yeah. So thank you so much, Dr. Shilpi, Dr. Agrawal, and the whole organizing committee to invite me here, and to talk about the Nobel Prize in Physiology and Medicine. And don't wait for my slides, because when I got the email from Shilpi and, she said, if you have slides, please share. So I found that if as an opportunity not to have the slides, right? So I thought it's better to have a dialogue rather than, I'm showing you some cartoons or explaining you by using slides. So starting with, what this Nobel Prize means, particularly when, Khushi mentioned that we have worked into this particular area of regulatory T cells. It actually gives you that, a proud feel that, a fantastic area which was actually discovered, which gave a huge opportunity to researchers in terms of both doing the fundamental research as well as, to look into its application, wide variety of domain of medicine. So I think starting with this crosstalk, our immune system is highly sophisticated, right? And it's still a paradox for us in terms of understanding various dialogues that happens in the human immune system. But immune system is also a very, very powerful, a defense system, right? Do you agree that, basically it's the immune system which helps us to protect us against various pathogens, right? Can someone give an example of the pathogens that you think that our immune system is actually tackling, particularly, post-pandemic? Yeah, virus, bacteria, a particular virus, which actually had really, gave us a tough time from 2021 to still, we are still looking at. What is that, the name of the virus? SARS coronavirus 2. Fantastic. COVID is the disease, right? So we call it COVID-19 virus, but it's a disease. Anyway, so the purpose to say is that, it's very strong defensive system for us. But if its activity remains unchecked, then it becomes destructive, right? Same, take an example of any war, right? If the army is still fighting, even if the war is over, what will happen? You will actually have a continuous, unchecked, uncontrolled phenomena that may lead to a disaster. In the same manner, this unchecked activity of our immune system has some process which it can allow to control. Now that is the question which the immunologist has been trying to address, that how our immune system at least decides when to stop, right? So this question was the one which of course remained a mystery. I will go back into a little bit of the historical perspective, but this was the question which was actually addressed by these three Nobel laureates, Marie Bronco, Fred Ramsdell, and Simon Sakaguchi. Two of them are coming from US, and the Simon comes from Japan. And they actually uncovered that how our immune system is actually kept, in control and actually checked for not doing any kind of overactivity. And this was pertain to a peripheral immune tolerance. Just keep that word in mind. I'll come why we call peripheral. Okay, peripheral immune tolerance, and it goes to a very specific type of T cells which have been coined the name regulatory T cells. Okay, there are a variety of T cells, but this is the subset which is called regulatory T cells, which led to the generation of peripheral immune tolerance, which is the subject of this Nobel Prize. So historically, until 1980, there was a theory which was called the clonal selection theory. Okay, that was given in around 1949, and the theory says that you have a thymus. In your thymus, there is a process of deletion of the T cells, which are called autoreactive. Right, the T cells, those who are going to target your own self tissues and the antigens in your body, are deleted in thymus, right? That's a process which was called central tolerance, right? So at that time, when Burnett and Fenner, they gave that theory, there were a few questions that despite of that deletion of those autoreactive T cells, we still have some of the autoreactive T cells that goes to the periphery. Thymus is always here, and we call periphery to all other organs below that. So when it goes to periphery, and we still do not have a destructive outcome of it. Okay, so the outcome of autoreactivity is an autoimmune condition. I will not go into the autoimmunity, we'll discuss that later, but this is a phenomena which is called autoimmunity. So then, there were always the groups asking that question that, is it the only thymus which is helping us to control, that overall reactivity of our immune system against ourselves, or there is something else? And that's where, this curiosity and the persistence comes into picture. The group from Shimon Sakaguchi from Tokyo. So in 1980s, he did a fantastic experiment. So he took a mouse, he deleted the thymus, and what he found, there is a huge autoimmune condition is happening in those mouse after the deletion of thymus. And he did additional experiment. He took the cells from a non-thymus deleted mouse, okay, whose thymus was perfectly intact, adult mouse, took the cells, the T cells, transferred into this thymus deleted mouse, and he showed, see, if I transfer these cells in a thymus deleted mouse, I am still able to control the autoimmune outcome, suggesting that the tolerance is just not happening only in thymus. There is something else which is happening outside of the thymus, which is protecting this autoimmune outcome or the autoreactivity of the T cells. But he just proposed it by doing some experiments. He was not having the answer that, what is those cells which are doing it, how it is happening, right? That's where sometime, so this is around 80s, then in 1995, he put a fantastic Journal of Immunology paper where he discovered that this is happening through a very specific subset of T cells which express a surface marker called CD25. So these CD25 expressing cells in a pool of all T cells are those who can control the autoimmune outcome in peripheral immune system without even having any interference from the thymus. So still, we immunologist always goes to the very highest granularity possible. We still didn't understand what, all these CD25 positive cells means. How do they differentiate, from where they come, right? Because everything generates in your thymus, all T cells come from there. So now the American connections comes into picture. The Mari Branco and Fred Ramstel, they were actually looking into a very interesting project of, it's called Manhattan Project. It was about the atomic bombs at that time in America. They were trying to understand, how the radiations affects human. Okay, so they were doing some experiments and they found a very uniquely, developed mouse, which was actually having a kind of disease where they have a huge glands because their immune system was completely uncontrolled. So they have a lot of, endocrinopathy, they have big glands, and they actually die very quickly within, 2 to 3 weeks because of that uncontrolled, immune reactions. So they did some experiments, they tried to understand why it is happening. And then they come down to a point where they found a gene, a transcription factor, which is called FOXP3, is the one which has mutations. And because of those mutations in that gene, the overall control of this immune system is not happening. And that's why those mouse are dying. At the same time, so they put this paper sometime in, so I'm coming from 1995, now this is 2001, it was a Nature paper or something, and Nature Genetics, I think. And then, pediatrician at the same time found that the same mutation also exists in humans, it's just not in mouse. So some of the kids, particularly males, they had this mutation leading to a disease called IPAX, which is an immune dysregulation polyendocrine disease. And they found that this is happening because of the same gene, which is FOXP3. And the mutation in that gene lead to this particular autoimmune condition. That's where Simon comes back. Then he realized, oh, this is what connects to my discovery of those CD25 cells, which were actually suppressing, any kind of overreactive immune system. He and others did the experiments and found it's the FOXP3 which controls those specialized and unique subset of T cells which are CD25 positive. And the FOXP3 became a master transcriptional regulation factor for this subset. So if you don't have FOXP3, these cells don't work. They lose their function completely. So this is how this discovery happens. And I think since then, there are a lot of fields which are now utilizing that knowledge in terms of its application. It has a huge application for cancer therapy, for autoimmune therapies, for variety of other cell-based therapies. A fantastic example in cancers is when you have a cancer, you have a lot of regulatory T cells that protects the cancer. They protect it so that our immune system don't attack it. So a way, if you can find to reduce these regulatory T cell subset in cancer, becomes a therapy, which got some Nobel Prize in 2018. The PD-1 checkpoint inhibitors. 2, in autoimmune disorders, you want to increase regulatory T cells, right? Because they actually control an overactivity of the immune system. So in autoimmune conditions, there are many drugs, many cell-based therapies which are already in the clinical trials. And I think in coming 2 to 3 years, we'll be seeing some of those candidates in clinic to control the autoimmune conditions like diabetes, lupus, SLEs, and others. And just adding to that, that understanding of regulatory T cells was even lead to some of those conditions which are not autoimmune but the alloimmune conditions. And that's where I was working when I was working in Institute Pasteur and Curie. We showed that by sending an antigen, I think many of you have heard of hemophilia, right? A bleeding disorder. So this happens because your factor 8 inner coagulation process doesn't work. You have a deficiency of it. So we showed that if we can introduce the factor 8 during the ontogeny of the immune system, during the pregnancy itself, in the very first stage of gestation, we can induce the tolerance against that particular molecule, and the therapy will never get the inhibitors generation. So that work was published in Science, and we also got a lot of recognition. It has been now patented, transferred to some of the companies in US, those who are working on developing the therapy utilizing that particular approach. So I think it is just one example that I gave, that how we utilize that knowledge and taken up to the applications. There are many other areas which these regulatory T cells have gone to. So just ending my conversation here by saying that its immune system is something which is it's not a binary phenomena. You still have to understand it's a dialogue, and that dialogue always requires a balance which is of course controlled by our own immune system, by the different factors which are actually present in the immune system. So with this, I'll stop here. Thank you so much for your time and attention. We're happy to address questions.
Questions, are there any?
Yeah.
So thank you so much for the inputs about the cells. So I have two questions. So like initially you were talking about like there is a very complex balance which is going on amongst the regulatory T cells. Like if we are enhancing it, we are treating the autoimmune diseases, while if we are suppressing it, it is actually to boost the anti-tumor activity. So like in the actual clinical settings, how close are we to this phenomenon that we are enhancing or suppressing the T regulatory cell activity, so that we could check that when we want to start the cancer therapies or when we want to see that we want to treat the autoimmune diseases?
Fantastic. A very interesting question. I think, I probably missed telling you that all these T cells have a kind of ID on it, right? Let's say it's me. I have an ID. My name is Nimesh, right? So every T cells will have a ID which is called TCR, a T cell receptor. Okay, and the T cell receptors is very unique for that particular subset. It will only recognize a particular antigen. So now coming to the role of Tregs in these two different conditions. In cancer, if you have to decrease it, you have to find a way to actually reduce only those Tregs which are specific to the cancer antigen, right? So we don't want to turn a scenario where we deplete all the Tregs and now we treat cancer, but we bring up the autoimmune disease, right? That's not what we want. So in cancer, the application of this Treg depletion has led to a very, a significant level now. Some of these checkpoint inhibitors are used, which actually allow to deplete the Tregs. So this has already been, gone to the clinic in cancer. In autoimmune diseases, increasing the Tregs have two different ways. One, either you use some modulators, which inside the human body can increase the Tregs. Again, we want to have the increase in Tregs which are specific to a particular antigen responsible for autoimmune disease, right? It becomes little tricky. We have not reached to a level where we can do that inside the human body. Still, the work is going on. But the other way around, where we can actually have the Tregs outside the human body and then expand them. That work has gone further ahead. And I think the two of the treatments, particularly utilizing IL-2, which is a cytokine for this CD25 receptor, is the one which has been used in the treatments. And it actually worked fantastically well, where we were able to increase the regulatory T cells in the autoimmune conditions. So in both the places, I think we probably will see more significant work in the next 4 to 5 years after this Nobel, because now the investment from government will also increase heavily, right, in terms of its application. So things will be on more the positive notes maybe in next few years.
So I have one more question.
Yeah.
So like you are also a virologist and I have a background from virology itself. So like many chronic viral diseases like be it HIV, hepatitis B or hepatitis C, they actually go and they regulate these T cells. They exploit these T cells because they want to cause the persistent infection inside our body. So I want to ask, like, if we could have a better mechanistic understanding of these T regulatory cells, so that we could find an antiviral by which we could stop the persistent infection of these viruses, because once they are inside, they are going to go and go work on these T regulatory cells. But if we somehow suddenly we develop some antiviral which could suppress the activity of Treg, so we might get a hold of the viral infection, but there is another chance that autoimmune disease might start working up. So like if there is any
so
exploratory
again,
mechanism.
I think this is again another good question in the same lines, that if we are able to find the depletion of virus specific clones of regulatory T cells, that's gonna help. Otherwise, we may generate then autoimmune conditions. So of course, reducing Tregs in case of persistent infection has not been yet tried, though some kind of CAR T cells therapy which has been done with the Tregs component, which has shown some potential. In addition to that, some of the conditions, particularly in vaccines, have been tried, where some molecules that can not allow regulatory T cells to reach to the lymph nodes to actually suppress a T cell activation has shown prominent vaccine responses, but it has not reached much ahead. Still, it is at a R&D level. So there is, of course, a kind of space there which one can look into, how one can reduce the regulatory T cells without affecting its physiological functions, but just specific to the virus infection. Yeah.
Forgive me for asking another question, but excellent talk.
Thank you.
And two questions. One is, how close are we to finding some kind of solution for cancer through this research? First question. Second is, you mentioned that the American government had funded the research and then it was commercialized. And you have also worked on Covaxin with government support, and then it was produced. How many such projects is government working on with you, because you know the Americans are making huge profits through this. I mean, their National Institute of Health funds all the basic research and the private companies profit. There's a book called $800 million Pill which elaborates on this. So are we also going to do something like that? I mean, not in terms of making super profits, but in terms of actually using the fundamental research that is being done to create desi products.
Yeah. So I think your first question about how close or how far we are with this particular technology or the particular knowledge in the cancer therapy, we are quite at a significant level now, because as I said, some of the immune checkpoint inhibitors helped suppressing the T cell activity. Some of the checkpoint modulators are coming up which want to increase the regulatory T cells in autoimmune conditions, as I said. So I think some of them are at a phase 2 trial levels. You can understand phase 1, phase 2 and phase 3. So some of them are already at a very high level of clinical trials, and we see that there is a good data coming out from those trials. So I think it will be very soon that we will have some molecules which are modulating regulatory T cells in both the cancer as well in the autoimmune condition. And your question 2, answer to that, I think in India post pandemic there is a huge change in the landscape of both research and application, and also the investment from government. I think we are probably doing much better than any European country in terms of the funding for R&D, for biomanufacturing, and even the programs that are related to its implementation. Taking out the fundamental concepts towards application, yes, that's what the job of some of the researchers, those who are working in the interface of these two areas, particularly the translational aspects. And I think there is also a lot of awareness about the patents. Now we know what we can patent, even the idea could be patented, and that patent can allow us to develop it very much specifically in-house within the country, right? That's what the idea, why you protect your ideas or your applications, your tools, whatever you have developed. So I think there's a lot of positivity around now in terms of the government investments in taking up these concepts towards doing some applications, where this ecosystem of startups has played a very significant role now, where they utilize this knowledge and want to develop some molecule. Maybe 99% of them may not work, but somewhere we have to try. So I think it's a good time for us to particularly taking these fundamental aspects towards translation.
Okay, thank you, Nimesh.
Thank
We'll
you.
move
Thank
on
you
now.
so much.
Thank you, Dr. Gupta, for a brilliant talk. Now, moving ahead, this year's Nobel Prize for Literature was awarded to Laszlo Krasznahorkai for his compelling and visionary oeuvre that, in the midst of apocalyptic terror, reaffirms the power of art. His work is known for its challenging philosophical prose and apocalyptic vision of modern life. To help us contextualize this powerful literary achievement, we have Professor Arjun Ghosh, a faculty member from Department of Humanities and Social Science at IIT Delhi, whose work is dedicated to the digital humanities, copyright and intellectual property, and the politics of performance. He is the author of several impactful books, including A History of the Jan Natya Manch, Plays for the People, and Freedom from Profit, eschewing copyright in resistance art. As the president of the Digital Humanities Alliance for Research and Teaching Innovations, Mr. Ghosh's perspective will connect literature, history, and the digital future. Please welcome Professor Arjun Ghosh with a warm round of applause.
So as you may have figured out, the previous 3 prizes were won by a team of researchers, or they may have worked independently, but the impact came as a in collective sort of. That's the community. But the literature prize is singular, because that's how authorship is conceptualized. And however, it's interesting to note that Krasznahorkai, I wonder why the other one word is missing there, but is also a screenwriter. He's not only a novelist, and he has his impact in the literary as well as cultural world has been also in collaboration with the Hungarian film director Bela Tar. Now, what I'm going to embark in is because in literature we do not we work with words, but work with images as well, created through words. But Krasnohorkai and Tar actually create images. So I'm going to do a little experiment which may or may not work. That is for you to see.
Moving on, finally, we arrive at the prize in economic sciences. The 2025 award was jointly given to Joel Mokir, Philip Agion, and Peter Howitt for explaining innovation driven economic growth. Their work, encompassing economic history and the theory of creative destruction, explains how continuous technological advancement drives modern prosperity. To analyze this critical framework for global prosperity, we welcome Professor Suma Athray, a faculty at School of Public Policy, IIT Delhi. With a DPhil from SPRU, University of Sussex, she has published over 60 papers and won multiple research grants. Her current research examines the role of AI in shaping the global economy and barriers to technology transfer. She has consulted for international bodies like the World Intellectual Property Organization and serves on the editorial boards of journals like Research Policy. Professor Athray's work directly informs policy on intellectual property and economic development worldwide. Please welcome Professor Athray with a big round of applause.
Thank you very much. Dear colleagues and students, I am so delighted to be giving this talk today on the 2025 Economics Nobel Prize. I'm delighted on two counts. First, because it validates some of the decisions we've taken as an institute. The School of Public Policy was established in order to study science and technology policy in India. So, this Nobel feels like a validation of that decision. And a more personal reason, because about 34 years ago, when I wanted to study technological change in India and its effect on growth, no economics department would give me admission for a PhD, not here and not abroad. So it is a great validation for this whole area of work where many scholars have toiled from and been, left to wander in different disciplines, that the Economics Nobel has recognized this as a legitimate area of economic study. So this pleases me much more than anything else. And by recognizing the study of technology as part of the economics literature, I think the Nobel Committee has achieved what leading journals found very hard to do. So as I say this, I also I'm mindful of the generosity of my colleagues in economics who allowed me to take the podium today and to speak about this topic, because I am trained in economics, but I've been studying technology policy for a very long time now. So with that preamble out of the way, which I really wanted to say because I was so delighted with this prize this year, I want to start by talking about this prize, which is awarded in equal parts to economists and an economic historian. Some might argue one half of the prize goes to the economic historian and the other half is divided between two quite traditional economists. So this continues something that the Nobel Prize has been doing now for the last 3 years. They first awarded a prize to Claudia Godian for her work on the economics of women's work, the role of gender in the economics of work. And then last year, we had the prize go to the institutionalists, Darren Acemoglu, Simon Johnson, and now this year we have the prize go to Joel Moker. Joel Moker is an economic historian, and a lot of what we understand about the role of technology in economic growth comes from the study of the of a couple of events. The Industrial Revolution is a very important one, but also the growth of America and Europe in the period after the Industrial Revolution. So, how did they catch up? What strategies did they use? And so on. So, economic history has really been more than just a description of events, but it has really given ideas, and it has been the main source of how we think technology affects economic development. So that's why the award, I think, is first and foremost recognizing the historical nature, the economic history of this whole area. So Joel Mokyr was awarded the prize for having identified the prerequisites for sustained growth through um, technological progress. So two slides motivate this very well. So here's a slide which is looking at Europe from 1300 right up to 1700, where there have been actually important inventions such as the printing press, the discovery of Newton's three laws of motion, the windmills, a technology that's coming back into fashion, heavy plows. But you can see that the growth of GDP per person, which is a common index of economic well-being, is kind of hovering around, it's almost constant, right? So that's very clear. So there's a comparison, not only there's a comparison between United Kingdom and Sweden in Europe, and you can see that it's moving very close to each other. But then if you just go a few years later, start at 1825, then something astonishing happens in Europe. You have the steam engine, which is of course discovered in 1780s, 1772. And then you have this cluster of inventions around the steam engine. Then you have the three-phase generator. You have now today artificial intelligence. But these are all big discoveries that lead to a cluster of applied inventions. And this is when the entire growth story also takes off. Okay, so that's very dramatic and very clear in these sort of simple time series looking at GDP per person. And so the question then is, why in 1825? So there are two types of questions here. Why in England and why in 1825, right? So why in England was a question that has been asked several times. We have got I think we have got so many different accounts of the Industrial Revolution. So that's not a surprising story. But what Mokyr asks is, why in England and not in China? Because China had access to a lot of very advanced technology before they discovered the gunpowder, they had discovered paper. Before the Chinese government decided to look inward, they were actually the leading technologists of the world. So the question is, okay, so why? And then the second part of the question is, why in 1825 and not in 1770, when some of the more dramatic inventions did take place? And his answer to this is that, well, so I want you to recognize, as scholars, we should all also appreciate the beauty of the argument. The beauty of his question and argument is that it's in history, it's very difficult to provide counterfactual, but he comes something close to it by taking this kind of comparative stance. So he's saying, look, there were other places in the world that something like this happened, but there was something that didn't work there, but worked in England. And so it's not exactly a counterfactual as we would use in science, but because you can't make history repeat. But the point is that he comes close to something like that. And I think that's something that's very elegant. And it's why it's a good argument, because though many historians had written, he's the only one who puts it in this form. So he identifies 4 factors or prerequisites for this kind of sustained takeoff due to technology. The first one he calls the flow of useful knowledge, because of the interplay between what he calls propositional and prescriptive knowledge. I mean, I should not have to labor this, because in IIT every day when we look at the buildings, we see a failure of this communication. But here is a nice graphic which explains it. So you have somebody building a bathtub according to a blueprint. So you can see that this person is toiling away with pieces of wood. He doesn't know exactly why they have to be arranged in that way, but he has a blueprint and he can build to that blueprint. And then you understand why bathtubs have to be large and have a certain volume of water because of Archimedes' principle. And of course, once that's known, you could apply this principle to several other areas of application and so on. We saw this also in the earlier lectures today when we talked about T cells, or when there was that wonderful presentation about drawing water from the environment. So, you know, this happens in every area of science, because once we advance a proposition, we know why it is true, and then we also know where else it can be applied, or the same logic could work. So there is a kind of positive feedback loop. So one affects the development of the other. So more detailed observations from prescriptive knowledge help us to arrive at a proposition. When you know why a proposition works, you can have better prescriptions and so on. So this is the first thing that he identifies, and it's very well analyzed in his book called The Gifts of Athena. But he also talks about why England. This was happening all over Europe. When he's asking about why England, he says, well, there was a combination of very different kinds of knowledge. There were people who were practitioners of prescription knowledge, like the skilled artisans and technicians. But there were also scientists and engineers willing to engage with those skilled artists and technicians. And there was also commerce lubricating the entire system. So there were people willing to put their capital into new ideas, new ways of doing things, and so on. He also talks about a culture of openness, sometimes both together. This combination of different types of knowledge goes along with a culture of openness. And he refers to the Republic of Letters, which is that in Europe, in the Victorian period, people would write to each other who they knew to be working on a similar field and take their criticism as as a good way to improve their work. And the people who were providing those comments also wanted that work to succeed. And this is the system on which modern day journal review processes are based, but it was happening just through letters. You may not know the person, but you know you're interested in the idea, so you come across this work of that other scientist and you write to them and take on board their comments. And all this is done gratis. It's not really paid for. And the last thing about why UK and not other countries is because the UK parliamentary system actually reduced political barriers. So UK was among the first. So every technology, or as Machiavelli told us several centuries ago, every inventor makes enemies because, well, they're not popular, because the people who their work will affect are their enemies anyway, and those whom their work will benefit don't know that it's going to benefit them. So every new technology creates a set of winners and losers. And in some countries, if the losers are in power, then those technologies may not have the possibility of attaining fruition or commercialization. But by having a political innovation such as the parliament, where you have different types of stakeholders who can negotiate a deal, so to say, UK was well placed to take advantage of those breakthroughs. So he identifies these four. Some people say three, but I think the second and the third are related but still distinct. He identifies these four conditions as being prerequisites for translating technology into economic growth, and that these things were present in England in the 1850s, in the Victorian period. So, this was my slide, which I've already talked about. So, in contrast to the work of Mouquer, Philippe Aghion and Peter Howitt attempt to describe mechanisms that link innovation to economic growth in any economy. So sustained economic growth is underpinned by improvements to productivity across different sectors. And we think that technological change is an important factor in influencing this productivity. So when asking When asking why increases in productivity come about in the economy as a whole, or put differently, what causes growth? Because ultimately, growth is sustained because productivity is increasing in the economy. You need fewer people to do the same job and get more out of the process. So if technology is a way, so if increases in productivity have come about because of technological innovation, which itself is a consequence of increases in R&D inputs, then the question to ask is, well, how did this productivity get distributed in the economy? Or put differently, is it the case that every new technology benefits everyone equally? Right? So think about something like ICT, right? So information and communication technologies, when they came onto the scene, affected a lot of different types of businesses, and each business probably could put in some more R&D and improve their business processes and achieve greater productivity and profits. In this kind of view of the world, the two technologies, the old and the new, are completely complementary to each other, right? So you have an input from a new technology, but this actually enhances the productivity of the old technology. And so there is not really any conflict. And that's the basis of several theories of growth, which are called endogenous growth theories. So the process of doing R&D gives rise to some technology which improves the productivity of all the processes and therefore improves productivity in the economy. And this is the kind of model, this is the kind of argument for which Paul Romer won the Nobel Prize a few years before. However, even as early as 1934, there was an economist called Schumpeter who had queried this. And the question is that this sort of complementarity of old and new inventions is actually not a given. In most cases, actually, new technologies replace the old, right? So this substitutive relationship was pointed out by Schumpeter, and I'll just give you an example. I think most people in this room will appreciate that. So there was a time when cameras used to be all SLR, right? Kodak was the leader of these kind of cameras, as was Canon. But then along came digital camera technology led by Fuji. Within a few years of this happening, Kodak had to shut down shop and leave the market, basically. And many technologies are evolved in this way through a process of competing for market share, and whoever wins destroys the competitor, right? So Schumpeter pointed out that this substitutive relationship gave rise to what he called perennial gales of creative destruction. So on one hand, you have a new technology, but it can only grow by replacing the old one, right? And when it happens, for some time, the person who produces that technology earns a huge profit. And this is the incentive for anybody to introduce that new technology. So you'll see everybody kind of swimming along, and then there's a person who brings up a new technology. He earns a lot of profit. And for a while, this steady state of growth is disturbed. There is growth because of the technology and because everybody is trying to copy it. And then once it's been copied by everybody in the economy, we go back. So you get a kind of punctuated equilibrium with spurts of growth, and you have life as usual till the next spurt of growth comes. So Schumpeter, in his account of creative destruction, put a lot of weight on the heroism of the entrepreneur who brings the invention, who bears the uncertainty, and who actually creates the conditions for this spurt of economic growth. Aghion and Howitt try to model this, but given the kind of constraints that are there in many economic models, where we have to assume a few things in order to be able to say something about the something precise about what is the mechanism that you're getting at. So in their model, and I'm not going to pretend to, it has a lot of different moving parts. And I don't think I can do justice to all of that. And of course, I'm also the last speaker, so I don't want you all to fall asleep. So the mechanism of growth with creative destruction is that an economy has firms with different productive capabilities. Okay. So the more able firms are at the top of this kind of ladder of capabilities, and they earn more profits because they are more able. So they earn these profits, they put more money in R&D in order to enhance the quality of their own inventions and products. So because of this, they're at the top of the ladder, they earn supernormal profits, and their technologies may be protected by patents. I heard quite a few people, especially Smita, querying patents. So technologies are protected by patents, but patents do not protect against new ideas. In other words, the market for new technologies and inventions is completely contestable. Anybody who has a good idea can come and try to produce a product based on that idea. So new firms can outcompete the firm at the top of the ladder and enjoy supernormal profits, and that's why, of course, they take the risk, because there is this lure of profits. But the incentive for R&D from new and old firms is slightly different, right? If the new firm wins or outcompetes the old firm, they get the whole market. If the old firm wins, they manage to increase their market a little bit and may not increase a lot of it. So the payoff to the old firm is slightly smaller than the payoff to the new firm, because the new firm will displace the old firm and take that market share. In their model, the money for R&D also comes from household savings. So, as interest rates are high, households will make the savings available for R&D, and therefore, this R&D will be invested in the new and old technologies. So this is the first macroeconomic model with creative destruction. So till then, all the other models of growth had mostly assumed a complementary relation. They didn't assume that new and old technologies are very substitutive to each other. So here's a very sort of nice illustration of it. So this is the lever of riches, which was the title of Mackay's book. And the lever of riches is technology. So you have this system of different gears where the household savings and interest rates together determined R&D. And then you have production, which is based on R&D. And you have other things like marketing and so on, which take you to the market and give the value added. So you can see that the government can lubricate this mechanism through its policy, or it can withhold it. So both are policies. And so the question is, when should it lubricate and when should it withhold? So Aghion and Howitt outlined two very divergent mechanisms. So they say that first, companies that are at the top of the ladder and invest in R&D also know that they can be outcompeted. This is some idea that there's just so much I can get out of a technology. Eventually, I'm going to run out of opportunity with this. Again, the Kodak and Fuji example is very useful, because Kodak had the first digital patents, but it chose not to use it because it didn't want to cannibalize its product. So management scholars call this disruptive innovation. And disruptive innovation is always problematic because firms don't know whether they should continue with what they have or should they rock the boat and gamble on an uncertain future. For society as a whole, however, old technologies have value. They have value because new knowledge builds on old knowledge. They also have value because, old technologies are employing a lot of workers. They don't want them to they don't want them to be out of jobs, and for a lot of different reasons. But so the private incentives for R&D by the incumbents are smaller than what would be their social benefit. Their social benefit depends on the usefulness of the old knowledge and also the number of people who are employed in that activity. And this is a very well-known public good argument for investing or giving subsidies to R&D, except now the reason is different. The reason is that incumbent firm may underinvest because they don't expect to gain so much from this technology. Okay. So in order to keep that technology going, we should give subsidies for investment. But there's the opposite side. which is that there can be too much of R&D. So new businesses are looking at profits to be made. Yeah. There's a business stealing effect, which means that they take over the business of the old firms and they may overinvest in new technologies. Sometimes it's known as R&D congestion. From a societal perspective, the new technology may only be marginally better, or we may be very uncertain about the effects of this technology. Think about AI currently. This is in this kind of situation. So the policy prescription then is there's already a lot of R&D going on. We don't know how useful it is. So let us not give it the subsidy. And that seems to be the model followed by the US. Because though AI is hyped as a very promising new technology, actually the US government is not subsidizing it. It's mostly being developed through through private capital. The other point which Aghion and Howitt make very strongly is that governments are too focused on jobs, but they should also focus on the worker. So workers that are in an old technology need to be retrained for the new one. There needs to be a safety net in order to allow them to do so. So that is in brief the two the two parts of the Nobel Prize. For further reading, please look at the summaries that have been produced by the Nobel Prize Committee. But also have a look at this overinvestment in R&D article, which explains when that happens. If I can, I'd like to take one more minute to say, well, those of you who found some of this material interesting should probably look at courses of study at both the School of Public Policy and Economics. And I put together this list from my knowledge of our courses. So both the courses on STI and sustainable development, and in the next semester, science, technology and development, which is taught by Ambuj, we do teach a lot of Mukher's work. It's a recommended reading. And next term, we also have a kind of trial course on the economics of innovation policy, which will go through some of these models. With the help of Abhijit Banerjee, I have also put together some relevant courses in economics. So these are the macroeconomics courses, which talk about growth theory, which is what Aghion and Howitt's model is, and also a new course that they are floating on industrial economics. So any questions about these courses, do come and ask us, but I would be delighted to have more takers for this in IIT. Thank you.
We are now open for questions if there are any.
Thank you so much. Thank you. I'm really delighted to know about your area of work, because this is an argument we've been making to our government consistently for several years, that technology, we must invest in technology to have higher economic growth. Just one question, because we've been using the justification of Robert Solow, who won the Nobel Prize, for proving that technology was the cause of economic growth between 1909 and 1949 in the United States. I'm not an economist. I didn't understand his thesis, but I understood his conclusion because it supported our own gut feeling about this. So how is this? And I just Googled it, and very few people have won Nobel Prizes on the issue of technology and economic growth. So how does this build on him, and how does this contribute to us, fighting for this cause in India? How is it different really from Robert Solow?
Okay.
Thank you.
So Solow is credited with the first growth models. So you can always achieve economic growth by applying more capital and labor, but at some point you'll run out of capital, or most probably you'll run out of labor first. So Solow had this insight that, well, you wouldn't run out if you could somehow find a way to increase the productivity. And the way to increase the productivity is actually technology. So that's why he won the prize. He did a lot of pioneering work in measurement of it. So till then, it had been believed that the limits to growth came from running out of labor. Because if you apply more labor and more capital, you can keep getting more growth out. But at some point, you'll run out of people to employ. And so that's when, That's why economics used to be also called the dismal science, because Malthus actually thought that this would happen. So Solo's great insight was that something will, technology can increase the productivity, and so we may not need to worry about the running out of labor, but now we need to worry about running out of technology. Both McCare and Aghion and Howitt are actually pointing to the mechanisms through which technology affects economic growth, beyond the simple application of labor and capital and increases in productivity. They're saying that in a real world, actually firms are competing, and innovation is a form of competition, right? So when they are competing, then a different kind of dynamics takes place, and that's what they Aghion and Howitt try to explain in their model. And what Joel Mokyr does is to give a broad framework for how could we understand this in terms of large epochal historical factors, because he's really talking about the period from 1825 up until AI. Okay. Why more work is not being done? I wish to know too, but
I think we'll continue the discussion over tea. Thank you, Suma. Thanks.
Can I ask a question this time? This side.
Can we really have this discussion outside when we're having tea? Who is it?
I will keep my answer very short.
Yeah, I just wanted to ask, is there an economic precondition to growth? So for instance, Mokyr talks about the marketplace of ideas in his work on the culture of growth, for instance. We talk about England is a place where the marketplace could thrive, but not a place like India, which we talk about as having 23% of the world GDP before the Britain came over. So is economic precondition a thing for technological growth, or is it the other way around?
So I am answering as I think Mokyr would have answered, and his argument is very clear. He feels that there are a lot of things that need to happen in a society in order for technology to translate into growth. In particular, he identifies these 4 kinds of prerequisites, right? These are not economic. These are more, I would say, cultural or something to do with how society is set up. So the flow of useful knowledge so that the prescriptive and propositional knowledge can talk to each other. That's for him a precondition. The combination, the ease of combining these different types of knowledge, commercial, technical, and scientific. A culture of openness, that, we are ready to embrace a new vision and see a new scientific principle and see how far we can go with it. So, and the removal of political barriers, which of course is very, very important when the economies are not growing. So it's not my opinion, but since I'm presenting his work, based on his work, this is what I conclude, that these are the preconditions you need. These are more socio-economic than purely economic.
Yeah, I get the point. So I was just asking, is there a way of quantifying some of these facts in terms of certain economic measures as a precondition? Yeah.
We can, but when we talk about growth and development, we are doing more than counting GDP, right? We are thinking of a lot of different factors. How healthy is the population? How easy is it to go to a doctor? Can somebody who grew up in poverty go to school? So these are not measurable by the kind of measures economists have devised to measure growth, right? So I think development is a much broader concept, and that's why the printing press was there in the slide, because many people would say that printing press was the first step. Because of the printing press, ideas were accessible to everybody, right? In India, for a long time, we've had the oral tradition. Printing press came only much later. And therefore, it's not very surprising that music, many of these cultural activities are organized in kind of family guilds, right? So I think, yeah, my feeling is that it also depends on the socioeconomic circumstances which have to be in place before. Okay.
Thanks again, Suma.
Thank you, ma'am. That brings us to the end of the session. We are honored to have with us Professor Rangan Banerjee, Director IIT Delhi. I would like to request him to please come up on stage for the closing remarks. Please give a big round of applause.
Thank you. I'm sorry that I missed the first 4 talks, and I realized that I really missed something when by hearing the last 2 talks, which was so enriching. I'd like to first of all thank all the speakers, 5 of our colleagues, as well as Ambassador Purushottam. You know, talking about a domain, a contribution, a Nobel laureate, someone's contribution, and making it intelligible for a generic audience is really, really takes some doing. So I'd like to thank all of you for doing that. I think lots of interesting things. We had the Venezuelan vice president coming to our campus. I was quite stunned by the level of security that was there. And also it was very interesting because the vice president actually was trying to see if her researchers from Venezuela could access our facilities. And we suddenly realized that they were denied, did not even have the standard characterization, fabrication equipment because they've been denied so many things. And of course, the Peace Prize has always been in the news recently and a lot of controversy. But for all the other prizes that we talked of in technology, the kind of things which you were talking of, it was delightful to see that it's not just innovation, but we are looking at technology and innovation as a public good. Again, a case for today when we talk about investing in science and technology, it is all about the immediate, there's a perception that everything will happen through market. And that innovation will happen through competition. But then long-term innovation has got to be a combination of things. And I think I was delighted to see also that, you had this plug finally about the courses. So it's good to have people relate this and come up with courses. I have a wish list that I hope sometime in the near future, we will have one of the Nobel laureates himself or herself from the institute making the presentation. So with this hope, I'd like to thank all of you for being such a good audience.
Thank you, sir, for your remarks. I would request you to please stay back for just a bit. I would like to request all of the speakers to please join us on stage and Dean R&D to present for a group photo and to present a token of gratitude from us. Please keep the applauses going.
It was very different presentation which he made, and nobody could say anything after that. Innovation is something we do, not only in technology but also in the presentation literature. Without slides, he explained so well. Everyone could get everything. Nothing amazing. Thank you so much. Thank you very much. So I have also been working in environment. But you explained it so well. Thank you so much.
I think that's it. Thank you all for joining us today. We have high tea arranged for all the speakers and the faculty and all the organizing staff at the first floor. And all the students are requested to exit through the right gate and collect their refreshments. Thank you. Thank you.